Welcome to the Deep Dive, where we take your sources and really extract those crucial nuggets of knowledge. Have you ever been in a long conversation, maybe trying to remember details from some complex document, and just wished your brain had a perfect rewind button? Or, just a better way to hold on to context from the very beginning? Well, today we're diving into how artificial intelligence tries to do just that, how machines actually learn to remember the past in sequences. Think your speech, text messages, even complex data patterns over time. We're going to explore recurrent neural networks, RNNs for short, and how a really clever architectural design, what we call gated units, specifically long short-term memory, or LSTMs, helps them tackle a huge challenge in deep learning, which is remembering vital information over long stretches within a sequence. It's all about giving AI this kind of long, short-term memory so it can really process how our words and data flow together instead of forgetting the start of a sentence by the time it reaches the end.
That's absolutely right. Our mission for this deep dive is really to unpack the core ideas behind these fascinating networks. We want to understand their significant applications, the tech you use every day, and, crucially, examine a fundamental problem they face, that forgetting issue you mentioned, and then look at how a brilliant innovation just transformed their capabilities. Our insights today, they come straight from foundational machine learning texts and interviews with leading AI researchers who've really shaped this field.
Okay, so to really get why these recurrent networks were such a breakthrough, we probably need to understand the basic challenge AI faced. When dealing with anything that has a sense of time or order, at their heart, neural networks are these computational structures, kind of inspired by the brain, right?
Yeah.
They have layers of interconnected units, they process information, and they learn to make predictions by adjusting their internal weights. That's how they learn from data, images, numbers, or, like we're focusing on, sequences. But here's the interesting bit. Imagine you're trying to understand, I don't know, a complex legal document, a recipe, or even just a simple sentence like, the quick brown fox jumps over the lazy dog. What happens if I just scramble those words all up?
Meaningless.
Exactly. The meaning is completely lost. A traditional neural network, often called a feed-forward network, might just treat each word or, say, soundbite as a totally independent input. And that clearly won't work for understanding meaning or context over time. You simply need to know what came before to understand what's happening now.
Precisely. And to really underline how vital this order is in machine learning, we actually call these sequences. A sequence isn't just like a random collection of data points. It's more like a matrix where each row is a feature vector, and the order of those rows matters tremendously.
A feature vector. Can you
Yeah.
maybe unpack that a little?
Sure. Think of a feature vector as just a concise numerical profile of a single item. So, for a word, it might represent its meaning, maybe its grammatical role, even its sound characteristics, all sort of condensed into numbers the computer can actually work with. So sentences become natural sequences of these word vectors, or maybe character vectors, and speech is a sequence of sound features. If a model doesn't account for that order, it just loses critical contextual information. It'll struggle with tasks that need an understanding of flow language, events unfolding kind of like trying to read a story with all the pages shuffled.
Right, that makes sense.
Yeah.
So how did researchers actually design networks to remember and use that information from previous steps? This seems like where the real ingenuity comes in.
It really was. To tackle this, researchers developed recurrent neural networks, the RNNs we mentioned. Unlike their simpler feed-forward cousins, RNNs are specifically designed to handle this sequential data. They do it by introducing a kind of hidden loop. Yeah, a loop that allows information to persist from one step in the sequence to the next. It's sort of like giving the network a short-term memory that carries over. It processes words one by one, but always keeps, let's say, a little note of what came before.
Okay, so it's reusing information.
Exactly. The core idea is that RNNs reuse information from previous steps in the sequence. This means they can do things like label, classify, or generate sequences. Imagine a network processing a sentence like, a little too dark for my taste. At each time step, so each word the network processes the current word while also considering its hidden units activations.
Hidden units activations, like its internal state.
Precisely. It's an internal state that encodes what it's processed so far, almost like the network's running mental summary or, a scratch pitch for the sentence. This lets the network build up an understanding of the entire sentence over time, word by word, gradually accumulating that context.
And once they cracked that, I bet the applications started appearing everywhere.
Oh, absolutely. RNNs became, as you'd guess, really widely used in text processing. Sentences, Whole documents, they're inherently sequences of words or characters, and for the same reason, they're used extensively in speech processing too.
Like sentiment analysis.
Yeah, good example. In sentiment analysis, an RNN can analyze each word in a review, but it's gradually building and encoding a representation of the entire sentence to figure out if the overall feeling is positive or negative. It's looking at the whole arc of the review, not just, spotting isolated words like good or bad.
Okay, and you also see this power in tasks like creating word embeddings, right? Things like word2vec.
You do. Techniques like Word2Vec, which, well, fundamentally it's a neural network, they learn to convert words into these numerical word vectors, and these vectors capture semantic relationships. So words with similar meanings like charm, wit, humor, they end up closer together in this kind of multidimensional space.
Which allows for those cool analogies.
That's the surprising part. It allows for abilities like solving analogies, such as man is to woman as king is to queen, just by doing vector arithmetic. Literally adding and subtracting these word vectors. It's quite remarkable when it works. Although it is worth noting, these analogy systems aren't perfect. Sometimes they give you really cryptic or, frankly, nonsensical results like, thirsty is to drink as tired as to drunk.
That's a fascinating example, actually, because it's not just a funny mistake, is it? It tells you something important. These systems are phenomenal at spotting statistical links, patterns, but they don't understand the world like we do.
Exactly.
It learned tired and drunk often appear together in texts, maybe, but not the causal link or the social context. So, okay, RNNs sound like they crack the sequence code, they carry context forward. Was that it? Or did new problems pop up?
Unfortunately, no, it wasn't the end of the story. A big step forward, yes, but standard RNNs ran into a pretty significant problem, especially when those sequences got really long. Think a long paragraph or an extended conversation. It's called the vanishing gradient problem.
Vanishing gradient. Okay. Sounds dramatic. What actually happens? Why does it vanish?
It does sound a bit dramatic, yeah. And it's a fundamental challenge in training deep neural networks generally, but it really hits RNNs hard when processing long sequences. See, networks learn by adjusting their weights, those internal dials, through a process called backpropagation.
Right. Learning from errors.
Kind of. Think of it as the network looking at its mistakes and trying to figure out how to tweak every decision it made along the way, going backwards to do better next time. The problem happens because as the network calculates how much to adjust the weights way back at the beginning of the sequence, based on an error much later, that learning signal gets repeatedly scaled down, multiplied by small numbers over and over.
Like shouting down a really long hallway.
That's a great analogy. By the time your voice or the learning signal reaches the start, it's just a whisper, almost gone. Mathematically, these gradient values, which guide the learning, they become incredibly tiny as they're propagated backward through many layers or, in RNN, many time steps. They effectively vanish. What this means in practice is that the initial layers or the really early inputs in a long sequence, they train incredibly slowly, if, they train at all. The network just can't learn from things that happened way back at the start.
Oh, wow. Okay. It really paints a picture, doesn't it? Like trying to understand that complex legal doc or a long scientific paper. But by the time you reach the end, you've completely forgotten the premise or key terms from page 1.
That's essentially it.
That's basically what happens to a standard RNN with this vanishing gradient. It struggles to maintain what researchers call long-term dependencies in the data. And that's a massive problem if you want AI to process anything more complex than a short sentence or really grasp the nuances of human language. Sounds like a real brick wall.
It was, for quite some time. This forgetting problem was a huge hurdle.
So what was the solution? How did AI get over this memory lapse? How did they fix the vanishing gradient?
The fix, or rather the breakthrough, came with what are called gated units. These are the really ingenious architectural components behind what became widely known as long short-term memory, or LSTMs. And later, some related ideas like gated recurrent units, GRUs. Interestingly, the original LSTM architecture, it was proposed way back in 1997.
97, wow.
Yeah, but its true potential wasn't widely realized until much later, well into the 2010s, when we had the computational power and the huge data sets needed to really make them shine. It was genuinely ahead of its time.
That's incredible. So invented in 97, but took off much later. What's the magic? What's the beauty of these gated units that made them so revolutionary?
Well, the beauty is they provide a much more sophisticated memory mechanism compared to standard RNNs. They essentially allow the network to store information in their units for future use, much like bits in a computer's memory. But, and this is key, unlike simple memory, The reading, writing, and erasure of information stored in each unit is controlled by special functions, these gates.
Gates, like gatekeepers for memory.
Exactly like that. They act as intelligent filters, not just simple on-off switches. Think of it like a sophisticated memory manager with basically three main controls. There's an input gate that decides which new information from the current step is important enough to let in. Then there's a forget gate that decides which old stored information is maybe no longer relevant and should be discarded, to avoid clutter. And finally, an output gate that decides what combination of the newly filtered input and the remaining old memory should be passed on as the memory for the very next step.
Okay, so it's not just passively holding on to everything, but actively managing what's important. Deciding what to keep, what to forget, what to use right now. That sounds incredibly powerful.
It is, precisely. This means a trained network can read the input sequence and decide at some early time step to keep specific information, crucially important information. And that preserved information about things that happened way earlier can later be used by the model to process the feature vectors from near the end of the sequence.
Ah, so it bridges the gap.
It bridges the gap, effectively solves the vanishing gradient problem for practical purposes. Those gates allow the learning signal, the gradient, to flow unimpeded over long distances when necessary. It prevents it from just fading away. It's like having, a secure, well-managed vault for critical information that you can access exactly when you need it, rather than just shouting into that echo chamber we talked about. This breakthrough was truly pivotal. It allowed RNNs to finally connect information across really long distances in a sequence, enabling AI to follow much longer, much more complex threads of information.
Yeah, this wasn't just like a minor tweak. It feels like it gave AI a completely new way to think about time and context within sequences. It unlocked capabilities that must have seemed like science fiction before. It really let the field climb a significant hill, as one researcher put it, didn't it? Opening up so many new possibilities.
Absolutely. These advances with gated RNNs, especially LSTMs, they've been fundamental to so many of the AI breakthroughs we've seen in recent years, particularly in natural language processing. Think about neural-machine translation services like Google Translate. They made astonishing strides. Google even claimed in 2016 they were bridging the gap between human and machine translation. Microsoft announced human parity for some language pairs, just showcasing the remarkable power of these systems to process and translate long, complex sentences with accuracy that was previously just unimaginable.
And beyond translation.
Oh, yeah. We see them in smart assistants, where understanding the flow of a conversation over multiple turns is critical, even in things like generating realistic music or predicting complex patterns in time series data, maybe for financial forecasting or medical diagnosis.
You mentioned human parity for some translation tasks, which just sounds incredible. But our sources also flag some pretty significant limitations that still exist, right? What are some of the most maybe frustrating or revealing errors these advanced systems still make, even with their improved memory?
That's true. While they've come an incredibly long way, they're definitely not perfect. Automated speech recognition, for example, is still not at human level. Background noise can really mess with accuracy, and unusual words or maybe ambiguous phrases can throw them off in ways that really highlight their lack of true understanding.
Like the examples in the source.
Yeah, the source gives great ones, like saying, mouse is my favorite dessert, but having it transcribe as moose is my favorite dessert, or the bareheaded man needed a hat, becoming the bareheaded man needed a hat.
Yeah.
Right. Still often just a surface level processing then.
Yeah.
What's causing those kinds of errors? What does it tell us about how these systems are actually thinking?
Exactly. Surface level is a good way to put it. These errors highlight a deeper issue. It's really a lack of genuine understanding. These systems primarily operate on patterns, statistics, probabilities learned from vast amounts of text. They don't have the underlying semantic knowledge or, common sense reasoning that lets us instantly distinguish moose from moose based on the context of dessert. Language is just inherently ambiguous. It's deeply dependent on context, and it assumes a ton of background knowledge that we humans just have. Current deep learning-based systems, they're really good at statistical learning, pattern recognition, and large-scale data analysis, but they don't go below the surface. They often lack other hallmarks of intelligence, like the ability to do counterfactual reasoning, thinking about what-if scenarios, or just basic common sense reasoning. They can mimic human language incredibly well, but they don't yet truly comprehend the meaning behind the words they process. They're amazing statistical engines, but not yet true thinkers.
It still sounds like we're talking about incredibly sophisticated mimicry rather than actual comprehension. Does this mean we need a fundamentally different approach to AI to get to genuine understanding? Or just, even better versions of what we have now, maybe with even more advanced memory structures?
Well, that is the million-dollar question in AI research right now, isn't it? Many researchers believe that while LSTMs and their successors like transformers, which maybe we can dive into another time, have taken us incredibly far with pattern recognition and remembering these complex sequences, achieving true common sense and real understanding might require a shift. Perhaps incorporating symbolic reasoning or other cognitive architectures. It might not just be about more data or bigger networks. It could be about fundamentally different ways of representing and processing knowledge altogether.
So wrapping up, what we've unpacked today is this really incredible journey of how AI evolved to handle sequential data. From struggling with basic memory and hitting that wall, the vanishing gradient problem, to building these complex models with gated units like LSTMs, models that can now remember important context over really long periods. These recurrent neural networks have truly transformed how AI processes information, like our speech and our text.
Absolutely. And while incredible progress has been made in giving machines this kind of memory for sequences, letting them process and act on information that unfolds over time, the next big frontier isn't just about storing more information for longer. It's about truly understanding its meaning, discerning subtle contexts, applying common sense, much more like humans do. These are the deeper, maybe steeper hills that AI researchers are climbing right now, moving beyond simply remembering the past.
And that definitely leaves us with a provocative thought to chew on. As these AI systems get better and better at remembering the past of our conversations, our data, and learn to handle ever longer sequences, what new forms of intelligence or maybe understanding do you think might emerge from that? Things we can't even foresee yet. Will better memory eventually lead to something closer to profound comprehension? Something to ponder until our next deep dive.